Okay, now that we've learned a little bit about Hess's law, we're going to learn how we can use what are called standard enthalpies of formation to find the enthalpy for almost any reaction that we want to know the enthalpy for. So this is really convenient. So first I want to define for you the standard enthalpy of formation. It's a big idea. So the standard enthalpy of formation. And again, this is a really helpful idea, a really helpful and tabulated value. There's a bunch of these that have been tabulated. And these tabulated values are going to help us find the enthalpy for just about any chemical reaction that we want to know about. This is symbolized in a particular way. You know, I've been symbolizing the enthalpy change for a reaction like this. If you see me or see it in the book where there's an enthalpy change for a reaction written with a little subscript down below that says an F, this refers specifically to the enthalpy of formation. And then if you see a subscripted 0, this means standard state. Something that's been measured under what we consider the standard way of doing our measurements. We got to sort of standardize the way that we write enthalpy reactions because they change based on temperature and pressure and other things like that. So we want to measure all of these at a particular temperature and a particular standard temperature and a particular standard pressure. Okay, so I'm going to write out the definition for this. This is the enthalpy change for the formation of something of 1 mole, I should say, 1 mole of a chemical from its component elements. And of course, since we're trying to do this under standard conditions, we need the way the elements are existing in their standard state. So we say that here. From the component elements at their standard states. There's a lot in here. There's a lot in here that we need to discuss. So the first thing I want to do is I want to say what the standard temperature and the standard pressure is. So this is all going to be measured at standard temperature. Which is 298.15 Kelvin. That's about room temperature. And it's going to be standard pressure. So standard pressure is 1 bar pressure. And a bar pressure is about atmospheric pressure. So the normal atmospheric pressure that we experience is, roughly speaking, 1 bar. And that would be atmospheric pressure at sea level. All right, there's a lot in here. So let's, for example, think about the formation of a compound. We'll say ammonia. Okay? We're going to make ammonia, NH3 gas. Now we're going to make NH3 gas, and we're going to make 1 mole of it. And we want to find the enthalpy change for this from its elements. What elements are we going to need to make ammonia? We'll just look at the atoms that are in there. I see some nitrogen and I see some hydrogen. Well, it'd be nice if we could just say, well, we're going to take 1 nitrogen atom and we're going to take 3 hydrogen atoms and we're going to react them to form this. And it'd be nice if we could do that. The problem is this really doesn't exist in any large extent pretty much anywhere. It's a pretty exotic chemical species. this is not the way that nitrogen as an element tends to exist. If you think about it, you might remember me telling you that nitrogen in the air exists as N2 gas. So there's two atoms of nitrogen that are connected together in a molecule, and that tends to be the way that nitrogen exists at room temperature and atmospheric pressure. And because this is the way that nitrogen exists primarily at this temperature and this pressure, we say this is nitrogen in its standard state. Now, you've seen me play around with some liquid nitrogen, and you've had the opportunity to do that in lab as well. And you should ask yourself, should this be N2 liquid? Is that the way nitrogen tends to behave at this temperature and this pressure? Of course not. Liquid nitrogen is really cold. We know that nitrogen at this temperature and this pressure exists as a gas. So when we're starting with our starting materials, when we're writing the formula, the chemical equation, I should say, for the formation of something from its elements in their standard states, we have to think about how that substance exists normally at the temperatures and the pressures that we normally experience, in the classroom. So this would be the appropriate way to list the element in its standard state for nitrogen. And it's going to be different for different elements, right? I mean, carbon at room temperature and room pressure is not a gas. That's going to be a solid. We'll get to that, though. How about for hydrogen? How does hydrogen tend to exist at this temperature and pressure? Well, you might remember that this is one of those substances that exists, like nitrogen, as a diatomic gas molecule. Diatomic meaning two atoms stuck together in a molecule. So I'm going to write here H2 gas, like that. That's how nitrogen exists, that's how hydrogen exists at room temperature and room pressure for the most part. So I've now got my elements. Those are going to be my starting materials. Anytime we're going to write an enthalpy of formation, we're always going to start with our elements in their standard states. And we're going to make 1 mole of the chemical that we're interested in. Well, this is going to be a little difficult because I've got an N2 over here, and I need to make 1 mole of this. Well, if I take a half mole of this, a half mole of N2 molecules gives me 1 mole of nitrogen atoms, which is what I need. Similarly, we can write 3 halves H2, because 3 halves of H2 molecules, if I take 3 halves of those, then I end up with 3 hydrogen atoms. So this would be the appropriate way to write the chemical equation that indicates the standard enthalpy of formation of ammonia. You make 1 mole of a product, of the product that you're interested in, ammonia in this case, and we make it from the elements in their standard states.